Hi, I'm Miranda. I'll be speaking about the smooth complexity of policy iteration for Markov decision processes. This is joint work with Mihalis Yannakakis. Suppose I told you that I have a super cool new algorithm. And what I mean by this is I tried my algorithm on a bunch of different inputs, and I saw that it produced the correct output very quickly on every input that I tried. And I want to convince you that my algorithm runs fast. Now, being furious, it's not enough that I just ran the algorithm a bunch of times and it seems like it runs quickly. What we actually want to do is we want to prove a formal statement about the algorithm's runtime. The first thing that we might try to do is analyze the algorithm's worst case complexity. So if we're able to show that in the worst case the algorithm runs in polynomial time, we would be pretty happy. But unfortunately, this might not be true. It might be the case that even though it ran quickly on every input I tried, there are a few very bad inputs on which it takes exponential time, so there might be an exponential lower bound, which wouldn't be great. But even in this scenario, we would still hope to be able to prove something that explains why the algorithm seems to run quickly in practice. And what we might turn to next is looking at the algorithm's average case complexity. So we might show that with respect to some specific distribution, the algorithm runs an expected polynomial time. And this is a little bit good, but it wouldn't be totally satisfactory because this specific distribution might be something like the uniform distribution, for example. And the uniform distribution doesn't necessarily capture the instances that we run into in practice. In practice, the instances that we run our algorithm on might be coming from some natural distribution that we don't know that much about. So ideally, we would want to say that our algorithm runs an expected polynomial time with respect to the natural distribution, but we don't really know what this is. And this leads us to the question that we focus on in this talk, which is formally, what does it mean for an algorithm to be fast? And you might have realized from the title that we'll be talking about smoothed analysis, which was introduced to sort of reconcile this gap between worst case and average case analysis and help to answer this question. But unfortunately, we show that smoothed analysis doesn't help resolve this question for the specific case of policy iteration, an algorithm that runs very quickly in practice for Markov decision processes. So our results are mostly lower bounds on the smooth complexity of different variants of policy iteration. Our main result is a sub-exponential lower bound on the smooth complexity of Howard's or greedy policy iteration. This is one of the main variants used in practice. We also show lower bounds on the smooth complexity of some other policy iteration variants. And finally, we show an exponential lower bound on the worst case complexity of another policy iteration variant. So in this talk, I'll start by introducing what a Markov decision process is, what policy iteration is, and what smoothed analysis is. And then finally, I'll be ready to give you an overview of our main result. So a Markov decision process is essentially a Markov chain where at certain states you have a choice of which transition to take. And shown here is a Markov decision process where the states are highlighted. Here we have states S, T1, T2, and this unlabeled state. And each state has at least one action. These are essentially the transitions of a Markov chain. Highlighted now is one of the actions from the state S. You can see that this action has reward R1. It goes to the state T1 with probability P, and it goes to the state T2 with the remaining probability 1 minus P. This other action from S goes to T2, collecting reward R2, and it goes to T2 with probability 1. So like these actions, all actions have rewards, which may be 0, and all actions have probabilities of reaching other states. So the probabilities might be 1 in the case of the action that goes from S to T2, or they might be P or 1 minus P in the case of this other action. And actions might have non-zero probability of reaching multiple, say more than 2 other states. So you could have an action from S that reaches T1, T2, and T3 with some probability. We call actions such as the one from S to T2 that have probability 1 deterministic actions, and the actions with non-zero probability of reaching multiple states, we call them probabilistic actions. Now, our goal when working with an MDP is usually to maximize some notion of reward. So here we want to maximize the total reward, which is the sum of rewards that we get if we start at some state, say S, and we continue walking through the MDP, following actions and collecting those rewards as time goes to infinity. More specifically, we want to find a policy pi that maximizes the value at each state, where pi specifies the action taken at every state. So pi is an assignment of actions to states. And the value of a state S given a policy pi is given by the slightly complicated formula that I'll try to explain, where the value under pi of S is equal to the reward obtained by taking the action from S specified by pi, plus a weighted sum of, or a weighted average of the values of the states that you can reach by taking that action. So this weighted average is the sum over all other states S prime of the probability of reaching that state given the action selected by the policy times the value of that state under the policy pi. And this formula represents the expected total reward that you would get by starting at the state S and following the transitions specified by pi, summing the incurred rewards as time goes to infinity as you walk through the MDP. And just to show you an example of this value function, here suppose that pi selects the highlighted action from S. So under this policy pi, the value of S would be equal to R1, the reward you get by taking that action, plus P times the value of T1, plus 1 minus P times the value of T2. And one thing I want to point out is the MDP shown here has this sync state that loops back to itself and gets no reward. This is sort of necessary when you're considering the total reward, because otherwise the total reward would go to infinity as you continue walking to infinity. So you're always going to need some sort of sync state that collects zero reward from its action to make sure that the problem is well defined. Now, some convenient facts that I sort of assumed but haven't said explicitly yet are, for one, for every time-dependent strategy, there's a global policy with greater or equal total reward. And what I mean by this is that it shouldn't be immediately obvious that when you're walking through the MDP, every time you arrive at S, you want to take the same action. And sort of implicitly, when I said our policy is an assignment of actions to states, I assumed that every time you reach S, you want to take the same action specified by pi. So that's the sense in which it's global. But you can imagine that sometimes when you get to S, you want to take its first action, and sometimes you want to take its second action. But it turns out that actually, for any such time-dependent strategy, there's a global policy, so a fixed assignment of actions to states that has at least that total reward. So we can sort of restrict our search space to these global policies rather than these time-dependent strategies. And another convenient fact is that there exists a global policy that simultaneously maximizes the value at every state. So there's a single pi that maximizes the value at S, T1, T2, and all other states in our MDP. And so what we're going to want to do is we're going to want to search for this optimal policy. And the way that we do this is using policy iteration. Now, policy iteration is a greedy algorithm. It was proposed by Howard, and it leverages the fact that a policy is optimal if and only if there are no value improving switches, where a value improving switch is a way for a state to change its action in a way that improves the value of that state. And it turns out that because of the way that value is defined, if you increase the value of one state, this will increase the values of all other states. So you don't have to worry about decreasing the value of some states by increasing the value at another. And so we're able to use this convenient fact by starting with some arbitrary policy pi and iteratively improving it by making value improving switches. So what we do is, starting with pi, we iterate through all of the states and just check by computing the value by switching its action if it can improve its value by switching its action. And then once we've learned all of the states whose values can be improved by switching their actions, we want to choose some subset of their actions to switch, and we do this according to some switching rule, which I'll get into a little bit later. And then we just update this policy by making these switches, and we're guaranteed to improve the value of all states in each of these iterations. And so eventually we'll arrive at total reward maximizing policy. And we'll know when we've arrived at this policy because we can check whether any of the states have value improving switches, and if it is optimal, then none of them will have value improving switches by our convenient fact. As I mentioned, policy iteration uses a switching rule to choose which state's actions to switch in each iteration. And here are several switching rules. They sort of fall into two categories. The first is single switch rules, where you switch exactly one state's action in each iteration. Some of these include simple, topological, and difference policy iteration. And there are also switching rules that involve switching multiple states' actions in each iteration. In particular, in this talk, we focus on Howard's or greedy policy iteration, where you switch all switchable states in each iteration. But we also need some sort of secondary rule, because even though we're switching all switchable states, a given state might have multiple actions that could increase its value. And so we need a way to choose between these actions. And we're always going to choose the action that maximizes appeal, where appeal is defined here. And so appeal is defined sort of similarly to value. Here, the appeal under a policy pi of taking an action A from a state S is equal to the reward incurred by taking that action, plus, again, a weighted average of the values of the states obtained by taking that action. But sort of crucially here, the value of these states is defined in terms of the policy pi, which might not necessarily involve taking the action A. So the appeal of an action A is essentially the total reward that you would get starting at S and taking A the first time you choose an action from S, and then the next time you arrive at S and every time going forward, you follow the policy pi. And now that I've told you about these switching rules, I can tell you what we know about their efficiency in the worst case. So for all of the switching rules that I mentioned, there are known lower bounds showing that policy iteration takes exponentially many iterations to arrive at an optimal policy. And you might have remembered that I said policy iteration is very fast in practice. So again, we have this problem where we have worst case exponential lower bounds, but still the algorithm is very fast. And so the challenge here is to prove something formal that explains this intuition for the algorithm being fast, despite these worst case lower bounds. And one place that we might want to look for inspiration is in the analysis of the simplex method, which very similarly had exponential worst case lower bounds known for many years, and also average case upper bounds. But there's this sort of gap between them. And it was resolved famously by the introduction of smoothed analysis by Spielman and Tang, and smoothed analysis lies between worst case and average case analysis. The way I like to think about this is, in the worst case, the adversary chooses the bad input. So if we think of the adversary as choosing a distribution, since we'll want to compare it to average case analysis, the average case is allowed to choose a distribution where all of the probability mass is on some bad input, shown here. But in the average case, the input is chosen randomly according to some distribution that we fix. So here I have the uniform distribution shown. In smoothed analysis, we don't want to let the adversary choose a distribution that has all of the probability mass on a bad input. So instead, what we do is we let the adversary choose a bad input, and then this input is perturbed randomly according to some distribution of polynomially bounded density. So we're basically adding a little bit of noise before the input is given to the algorithm that smoothens the bad distribution that the adversary gets to choose. And so this is a sort of worst case expected runtime where the adversary gets to choose its bad input of choice, and then it's turned into a distribution of polynomially bounded density. And the smooth complexity of the algorithm is its expected runtime on this resulting distribution. And famously, Spielman and Tang were able to show that the simplex algorithm has polynomial smooth complexity. And so if you believe that instances that you see in practice come from a smooth distribution, then the fact that it has polynomial smooth complexity says that in practice, we expect the algorithm to run in polynomial time. And so this was a huge success of smooth analysis. And naturally, the question to ask in our setting is whether policy iteration, given its similar gap between its worst case and average case runtime, has polynomial smooth complexity. And unfortunately, we show that this is not the case by showing the sub-exponential lower bound for Howard's or greedy policy iteration and our exponential lower bounds for the single switch switching rules. So now I'll give you an overview of our main result, which is the sub-exponential lower bound for Howard's policy iteration, where you switch all of the switchable nodes. One thing I want to point out is that our lower bounds are actually stronger than is required just to prove that the smooth complexity is sub-exponential. We actually show that there exists a polynomial p such that for any perturbations of up to 1 over p of n, policy iteration takes sub-exponential time. So what this means is that after the adversary chooses its bad input, the algorithm is allowed to choose any nearby input within this 1 over p of n radius. And the algorithm, even on this input of choice, still takes sub-exponential time. So we basically give a bad input where an entire neighborhood around it is bad. So I'm going to give you an overview of how we show our lower bound. And the way I'll do it is by presenting our very complicated construction broken down into sort of 3 different steps. So first, I'll give you a high-level overview and show you how it simulates a binary counter. Then I'm going to zoom in and show you the structure of an individual bit in this counter. And finally, I'll show you how we introduce a gadget to accommodate perturbations. So in the first 2 parts, we're not going to consider the perturbations at all. And then in the 3rd step, I'll show how we deal with the perturbations. Shown here is the structure of our MDP, which simulates a binary counter, where the highlighted nodes represent bits. And the bits in particular have 2 actions. One is labeled 0, and one is labeled 1. And when we show our lower bound, we're going to start with a policy where all of these bits start by selecting their 0 actions, and they all want to switch to their 1 action. So the optimal policy that we're trying to find is the policy where all of these bits select their actions 1. And we enforced, using the structure of our MDP, that a bit b sub I can only switch to 1 when all lower bits have already switched to 1. So right now, b sub I can switch to 1 because b1 and all lower bits have selected 1, so it does so. And then we also enforced in our structure that when a higher bit, bi switches to 1, all lower bits, such as b1 here, switch to 0. And so this makes it so that policy iteration on our MDP simulates a binary counter. Now, the way that we actually make sure that this behavior happens is we introduce a bunch of extra actions at each bit. So shown here is the structure of a bit in our MDP. And we want to delay higher bits from switching to 1. Remember I said that b sub I can only switch to 1 once all lower bits have switched to 1. And all of these extra actions that you see in our diagram on the right are exactly how we achieve this. And the idea behind this is that we make the appeal of switching to 1 very small, remembering that greedy policy iteration always selects the action with the greatest appeal. And the way that we make this appeal small without actually decreasing the value is we introduce this self loop on the highlighted action that goes back to BI with very high probability 1 minus alpha. And remembering our formula for the appeal, here we have that the appeal of BI switching to action 1 is equal to 1 minus alpha times the value of BI plus alpha times the value of BI plus. And by making alpha very, very small, we can make this appeal arbitrarily close to the value of BI. So even though switching to 1 would actually earn a very large reward, R of I, by choosing alpha to be very small, we can make it seem like the reward earned would be small, even though it would actually be large. And so once we've made the appeal of action 1 very small, we can add many other actions that have higher appeal, but result in smaller increases in value when they're switched to. And these actions are just here to delay BI from switching to action 1. So what happens is BI will have to iterate through all of these highlighted actions here, which each increase its value by very little, but have much higher appeal, before it's able to switch to action 1. And we also make it so that whenever a higher bit switches to its action 1, BI switches to this highlighted action WI, which effectively restarts its cycle through these highlighted actions. And so this makes it so that before BI can switch to 1, it again has to iterate through all of these actions. And finally, we make it so that higher bits have more of these actions than lower bits, and so higher bits are delayed longer before they can switch to their actions 1. And this is how we make sure that BI can't switch to 1 until all lower bits have switched to 1, because BI will still be cycling through these highlighted actions. Now, so far, I haven't considered perturbations in describing our construction. And one problem, what I've talked about so far, is that we chose this alpha and lowering the appeal of action 1 to be arbitrarily small. And in fact, for our construction to work, alpha needs to be exponentially small. But if you remember, in our smooth analysis setting, we're considering inverse polynomial perturbations. And so with high probability, alpha will not be exponentially small, it'll only be polynomially small. So these perturbations might make alpha too large. And what we end up doing to solve this problem is we introduce a gadget to construct an exponentially small alpha, while the true probabilities are really only polynomially small, allowing us to accommodate these perturbations. So remember that the way that alpha was used is we had this self loop that went back to a state with probability 1 minus alpha and continued on here to y with a small probability alpha. And the gadget that we use to artificially make alpha exponentially small takes the following structure, where we add a bunch of intermediate states between x and y. Here they're the v sub i's, and each of these states has a probability, or each of these states' actions has a probability 1 minus q sub I of going back to x, and only continues to the next state with probability q sub I. So in order to get from x to y, we're going to have to get lucky. This happens with only probability, the product of the q sub i's, which by introducing k intermediate states, we can make to be exponentially small in k. So the probability of continuing all the way from x to y will only be 2 to the minus k. And so by adding this structure in place of that action that went to y with probability alpha before, we're able to construct effectively an exponentially small alpha here, even if the q sub i's are all only a constant. And you might have noticed that our diagram has this reward r for the action going from x to v1, and actually this gadget also lets us construct exponentially large rewards. In fact, if we have k intermediate states, then it turns out that we can simulate a reward of value 2 to the k times r. So by setting r to 1, we can simulate a reward that's roughly 2 to the k. And we use this idea in our construction as well. So when we accommodate perturbations, we set the actual parameters in our construction to all be polynomially bounded, both the rewards and the transition probabilities. And we use gadgets just like the one I showed you to simulate exponentially large and exponentially small rewards. And then finally, once we achieve this robustness to perturbations, this lets us use our construction to show a worst case lower bound for a slightly different objective called the reachability objective, which doesn't aim to maximize the total reward over time. Instead, you're trying to maximize the probability of reaching some special state. Because these objectives are slightly different, we need this robustness to translate between them. So thanks for listening. If you want to see the full details, our paper is available on arXiv.